Notes 9.5 are on the alternating series test and the error bound. Given an alternating series, you need to check to make sure the series satisfies two conditions for it to be convergent. The first condition listed here indicates that the terms are decreasing. When we can, we will check the nth term against the n plus 1th term to see if the terms are decreasing. If that is not a good approach, then we can look at the series as a function and take the first derivative. If the first derivative is positive, then the terms would be increasing. If the first derivative is negative, then the terms would be decreasing. In the second condition, we're checking to see if the terms are decreasing towards 0 specifically. We have taken limits on series recently, and they've approached other numbers than 0, like they've approached 1 or they've approached a half. So we're going to check to see if they're decreasing towards 0 specifically. Now, if either of these conditions fail, that does not automatically mean that the series is divergent. So we would have to go to another test to look at that. This test is checking for convergence. Let's start with our first example. For our first example, we're going to work on condition number 1 first. If I wanted to check for decreasing terms, I'd be interested in comparing n over e to the n as my nth term with the n plus 1 term, but that's not so easy to do. So what I'm going to do is consider the related function, x over e to the x. In doing this, I can take the derivative and find f prime of x. It is a quotient rule, so e to the x minus x e to the x over e to the 2x. That reduces to 1 minus x over e to the x. Now, the denominator of that result will always be positive, but the numerator can be negative. 1 minus x over e to the x is negative for x greater than 1, and that is what we're interested in. Therefore, f of x is decreasing on the interval from 1 to infinity. This shows that f of n plus 1 is less than f of n, and that means that our terms are decreasing. So b sub n plus 1, or the next term, is less than b sub n when n is greater than 1. Condition 1 has been met. Let's check condition 2. We will take the limit as n approaches infinity on the nth term, n over e to the n. In doing so, I will need to consider the related function as x goes to infinity of x over e to the x, because there is an infinity over infinity situation. So we have an indeterminate form happening when we take the limit. Therefore, I'm going to have to apply L'Hopital's rule to this and take a derivative in the numerator, which gets me 1, take a derivative in the denominator, which is e to the x. Now I can successfully take the limit, and I'm getting 0. So that means the second condition is satisfied. Both conditions of the alternating series test are satisfied, therefore the series converges by the alternating series test. On page 695, you would find example 3. Example 3 in our book goes through very similar steps as that example. So if you would like to see another example of exactly that kind, then turn to page 695 and read example 3. Our next series is an alternating series. Notice how our alternating pieces in the numerator, that leaves a 1 on top for the nth term, and our nth term is 1 over n. Do you recognize the nth term, 1 over n, as the harmonic? Well, when you take the harmonic and you put the alternating component in, this is called an alternating harmonic. Let's see if the alternating harmonic is divergent, just like the non-alternating harmonic is divergent. Condition 1, we're going to check to see if the terms are decreasing. In this example, it's rather easy to check our nth term, 1 over n, with the n plus 1 term. So I'm going to compare 1 over n to 1 over n plus 1. I simply replaced n with n plus 1. So 1 over n compared to 1 over n plus 1. The denominator of the second one is bigger. So if the denominator is bigger, that makes the fraction smaller. Our nth term is greater than the next term. Therefore, the next term is less than or equal to the nth term for all n. The first condition has been satisfied, and this is how you write that it's been satisfied. Second condition is take the limit as n goes to infinity on the nth term. Very simply, that equals 0, and that's what we were checking for. Do the terms decrease towards 0? And they do. Therefore, this series converges by the alternating series test. Two tips for you at this point. I'm writing alternating series test out completely because I'm explaining this to you, but from now on you could use the abbreviation AST, and that means your teacher and the AP graders will know what you're talking about, so that'll save you some time. The second tip is this. You may have noticed that knowing the harmonic is divergent has been helpful. Well, now you know that the alternating harmonic is convergent, so that will be useful also. Let's practice one more. If you are feeling confident, perhaps you want to pause the video and look at this example. Check the two conditions of the alternating series test and determine if this series is converging. If you want to do that, pause the video now, and I will go over the solution in a moment. Condition 1. This is not an easy nth term to compare with the n plus 1 term. I'm going to consider this term as a function. That allows me to take the derivative. Quotient rule again. The result is a fraction that is always positive. We have a 1 in the numerator, which is always positive, and we have a quantity squared in the denominator, which is always positive. This derivative is positive for all x. Therefore, f of x is increasing, and that means our next term will be greater than the term we're on. So our nth term will be smaller than our next term, and we were looking for the terms to decrease, and they are not. So condition 1 has not been satisfied of the alternating series test. That means the test is inconclusive. That does not prove divergence. If we look at the nth term test on the nth term n over n plus 1, the limit as n goes to infinity on n over n plus 1 equals 1, which means that's not equal to 0. Therefore, the series is divergent. Let's take a quick look at the terms of that series on the graphing calculator. Notice how the values either approach +1 or approach -1. So they just bounce back and forth and they don't approach a limit. This is a visual of a series that is divergent. In order to find the sum of an infinite series, you work with the partial sum. The partial sum of any convergent series can be used as approximation to the total sum. If you do an approximation, however, an approximation is not helpful unless you know how accurate your approximation is. So we calculate an error whenever we do an approximation, and that'll give us an idea of how good an approximation we have. That approximation is called the remainder after we do a subtraction. So this S represents the actual sum of the series, and this S sub n represents the partial sum. And the interesting thing about alternating series is this, that the bound on the error, or the biggest the error can get, if I could explain a bound in that fashion, the biggest an error can get is the next term. Look at that notation. B sub n plus 1 represents the next term. And we're telling you that it's the absolute value of the next term. Because we are dealing with alternating series, it could be that that next term has a negative on it or a subtraction in front of it. But we're talking about a quantity, like how far off our calculation is. So we don't care about it being negative. We just care about the magnitude of that difference. And therefore, we refer to the next term in its absolute value form, and it is considered the bound on the error in this approximation. Okay, I hope that made sense. Let's look at the actual theorem itself. Here's the theorem itself. If you have your series, and your terms are positive, the sum of the series has to satisfy the alternating series test first. So we're going to have to perform the test again, and then we can conclude our error bound as the next term. Now, we can put this in other words. The alternating series error bound is less than the absolute value of the first omitted term. So I'd like to remind you that a partial sum, we're taking the terms b sub 1 and adding term b sub 2 and adding term b sub 3. Now these things are alternating, so it could be negative here, and so forth. So if you decide just to take the first 4 terms, then the next term, b sub 5, is omitted. You're not using it in your sum. So that's what is meant by the first omitted term. And that's the next term notation I was pointing at up at the top. Okay, so we're going to get a series now, and we'll check the alternating series test to see if it's converging. So we know it is, we're being told that, and we'll just verify it. And then we'll decide how many terms it'll take to have a certain amount of accuracy. So here it is, our accuracy is to 4 decimal places. First, we're going to check with the first condition. First condition, if you recall, is to see if the terms are decreasing. And in this situation, it is fine to think of the n plus 1 term. I'm going to compare our nth term, 1 over n to the 6th, with the next term, 1 over n plus 1 to the 6th. See how I replaced n with n plus 1? And the reason why this is easy to use now is because the numerators are the same. So really the only comparison I need to look at are the denominators. What I have here is our nth term denominator is smaller than the next term. So if our denominator is smaller, that makes our fraction bigger. So the nth term is greater than the next term, and this shows that our terms are decreasing. So I'm going to write, therefore, b sub n plus 1 is less than or equal to b sub n for all n. That's how you tell us that it satisfied condition 1. Condition 2 will take a limit as n goes to infinity on the nth term to see if the limit equals 0. We're trying to see if the terms tend towards 0 specifically. And it's true, they do when I take the limit. Therefore, this series converges by the alternating series test. To look at accuracy, write out the first few terms. Let n equal 1, let n equal 2, let n equal 3. You're going to need your calculator. Let n equal 4, let n equal 5, let n equal 6. You might need more You might not need this many, but if you have your calculator, you can generate a few terms. What I need my calculator for is to check the decimal version of these numbers. I'm going to notice for you right now that the fifth term, b sub 5, the 1 over 15,625, as a decimal, that has 4 zeros, 6, 4. That is actually still bigger than the accuracy we've been told to look for. So I'm going to go ahead and look at the decimal for the next term, 1 over 46,656. That decimal has 4 zeros, but then we have digits 2, 1, 4. This is more accurate than we needed. If you read the alternating series error-bound theorem, we know that the error-bound is the difference between the actual sum and the partial sum we're looking for. We're looking for the fifth partial sum in this situation. Now we know that the fifth partial sum is going to be less than the sixth term, which is the first omitted term, according to the theorem. And the sixth term, b sub 6, look at b sub 6. b sub 6 is less than the accuracy we were looking for. Since the sixth term is less than the desired error, we just need the first 5 terms to get the desired accuracy. I have one more example so that you can take a turn trying to do this. Remember, when you start looking for error bound, you first have to confirm that the series is convergent. So you're going to check it with the 2 conditions of the alternating series test first. So please pause the video, try this last example, then turn the video back on to check your answer. I can tell that the nth term denominator is smaller than the next term's denominator. So if this denominator is smaller, that means the whole fraction is bigger.